All right. Well, welcome again. And who knows what week we're in. I keep thinking about it each time. And now it's, I guess, time to start counting down. I'll figure that out next. And so, as you know, you've already taken the second test. And we're getting close to that third test. Because it's third test in, I think, just a couple of weeks. In fact, I guess we could do the math. I think this week we have a holiday. Because you don't realize. Friday is the Veterans Day, and then we have a full week, but then we have the Thanksgiving week, which is only a partial week. I don't think that affects our class because it doesn't affect our class. Yeah, so there won't be a 199 this week. Because then I think, if I remember right, we got Thanksgiving and then one more week of instructions and then 1 week of finals. I'll have to look that up and start counting down here. But anyways, welcome back. We're getting close to the end. Although we're in the hardest material, I think, of the semester. Go on in here. And we're doing these two long chapters, 9 and 10. And the goal here today is to wrap up number 10 here. Give you the last piece of connections. I started my table over here again. What's the connection between the linear stuff and the rotational stuff? Same hint I gave you before. Your best bet to handle these problems is to ask yourself, what would you have done had this been a question about linear motion instead of rotational motion? What would you have done? And so ask that same thing, would you have done it using conservation of energy? Okay, well, use conservation of energy again. Just use it in terms of rotation. Would you have done it with a free body diagram and Newton's second law? Fine. If that's the way, then draw a free body diagram. Of course, our free body diagrams will have to do with things rotating. So that was the hint I was giving you. Couple more comments about this chapter, and then I'll do example problems. And you have a really good example problem in the lab today. If lab makes sense today, you're doing well. Chances are it might be a little challenging in the lab, and because we're going to do this moment of inertia. So, which is good. Maybe a little long, maybe that's not so good, but good that it's going to be a lab that, in the past anyways, students have come in, not have read chapter 10 or not have done much on chapter 10, and you can tell that by the lab, so they struggle through and get through the lab, but they learn a lot then in terms of chapter 10. Anyway, so that may be the case for you today. But like I said, good problem here. And I'm just going to do a bunch of example ones. And then we'll go into chapter 11. I don't see a starting chapter 11 here, but I will say this. Chapter 11, 12, two small chapters. So we just had two long ones. We're now about to do two short ones. Then we have the third test. And then I think we just got a quick two chapters after that. And then the final exam. So getting close to the end, but still some significant work to do here. So here's where we left off. We left off all with this idea of torque. Maybe I'll start over here in the chart. Here's this little chart. Every time you think about force, which of course is measured in newtons, then compare that to torque. And so I had left off with this idea. I had walked over here and I said, look, what if I wanted to open this door? To open the door, do I need a force or a torque? It's a torque because the door is going to pivot. The door is going to rotate. It's set on a hinge or hinges, and it pivots as it opens. So we're talking about how much torque do you need to open the door, not how much force do you need to open the door. Did you catch that? And then we went on to do this, and we drew this little picture over here, and we said, okay, let's say that we had some kind of object that we wanted to rotate, and I just had a bolt, a hex head on a bolt, and said, okay, now put a wrench on this. And so you put a wrench here, something like that, and you grab the wrench and you apply a force to it, call it F here for a moment. And the idea is to get it to rotate around the axis there. And so what we said is look at this force and look at that force. That is, we could take this total force and break it into its pieces. We might say this much of the force is perpendicular and this much of the force is parallel. Well, what do we mean by perpendicular? Perpendicular, I mean if I were to draw a distance arm out, or position vector out from the rotational axis out to that point where that force is acting. So in other words, where I'm holding my hand here. Then this amount of the force is perpendicular to that position vector, that distance vector. Right, that's the part that turns the bolt. This part of the force, F parallel, does not help this bolt turn in any way. Or doesn't even stop it from turning if it was already turning. So the part of this force here that is parallel to this position vector is useless in the sense of making something rotate. It would be like me standing over here on this door and saying, hey, I'm going to open this door. So I grab the handle and I pull it towards me. Does that open the door? I mean, I could pull as hard as I want here. It's useless pulling this way trying to open the door. I want to push perpendicular to the door. And as we pointed out, that it makes a difference on how much distance you have. And so when you're close, you got to apply a large force because your distance is small. And then, of course, if your angle is off, that affects it too. So where we left off was this. We said then the torque on three factors. The first factor is how much force do you have? Oh, and I should pause there. I used a phi. Did we use a phi or a theta? I used a theta last time, and I think this edition of the book uses a theta. So I want to be consistent with the book. Oh, no, I see a phi there. And it might be hard to be consistent because the book may not be consistent. Oh, I got a phi here. Of course, this is the 7th edition. Anybody look at the 8th edition? They use a phi? I think they use a phi. It's actually a good choice to use a phi because a theta we've been using for how much does the object rotate, and so we don't confuse it. In other words, if this then is my picture, then this angle here becomes the phi. What is the angle between the force and then the lever arm, if you will? In other words, this angle here is the phi. And so the part of the force that I want is phi sine of this hypotenuse, so that what I can get is how much is perpendicular. And so it's nice to talk about in phi. Now, if the bolt actually moves, then there will be a rotation to this bolt. And that's why I said it's probably better not to call that angle theta, only because this is what we've been using for theta. And but as you know, we don't always have enough symbols to keep things clear here. But something like this, where we've got two different angles, it's probably better to use two different symbols, especially for the beginning student. So I'm glad the author put a phi there, and I will too, instead of the theta there. But I did want to point out then the same thing that where we left, and this is the last big thing of the chapter, what we had on Wednesday here, is the torque then depends on those three factors. How much force do you apply? What distance do you apply that force? And then at what angle do you apply those force? Those three factors come into play. And I will tell you, as I said, I think the hardest thing of this chapter, and I think this is one of the hardest chapters of the semester, is realizing that torque is more than force. And that torque needs not just a force, but also a distance and also an angle. And also the same thing with that moments of inertia that we did so many calculations on Wednesday. That moments of inertia is more complicated than just regular inertia, and then what's involved when you do it, and we had those integrals that we had to do. And so these are the two pieces that I wanted to spend the most time in this chapter, just because they're a little more complicated here. What I didn't do, at least I don't think I got to, was asking this question on Wednesday then, what are the units? What units do we use here for torque? Now once you see the layout here, I think you know the answer. I think I heard it. What'd you say? Yeah, it's a Newton and a meter. And there's the distance in meters, there's the force in newtons. And so I'll put it over here in our little chart and say, okay, what we have then is the units of a Newton meter. And so we've got, units that are different than force, as it should be. Just like the units for moments of inertia was different than the units for inertia. And just like the units for rotational speed was different than the units for linear speed. All these should have different units. So I like to put them over here in this long chart that we've been making. I do want to pause though and say, wait a minute, haven't we seen these units before, Newton meter? What do we call it? Well, we call it the quantity work, but the units were called a joule, right? Don't call this a joule. This is not a joule. Let me demonstrate. If you were to turn this wrench here, then yes, there would be a distance it moved. And this distance would be measured in meters. And if you went to calculate the work would be force times the distance. And we might call the distance S for an arc length as it moved along an arc. But do you see how this distance of the arc that it moves in the direction of the force is different than this distance, the lever arm? These are different distances. These are different quantities. One is the quantity of how much work is done on that bolt when you turn it. The other one is how much torque have you applied to that bolt. And to keep those straight in our minds, here's what we're going to do. We are going to call torque a Newton meter and never call it a joule. Because you start calling it a joule, then you start thinking you're talking about energy or work, and we're not. And so that's the key recipe here. And so those of you who had me for 102 might remember that. I emphasized that back in 102. Torques are measured in Newton's meter. Never call it a joule. You start calling it a joule, and you're going to start confusing it with work and energy, and that's how we keep it away from it. So, again, don't call a Newton meter a joule, but the same thing, don't call a joule Newton meter. I know they're mathematically equivalent, and sometimes during the mathematical process you got to break down the units and simplify the units by calling a joule a Newton meter, and that's fine because that's what it is equal to, but it's a different distance, and so that's how we can distinguish. In fact, many of you have probably come into this class probably using wrenches and tightening bolts, and so, but you probably did it in the English system. In the English system, what do we use for the units of torque? Foot-pounds, right? So in the English system, what do they use for energy? Pound-foot. Right? So we can distinguish the two. Now, it's not very common, so you may not be familiar with that, whereas foot-pounds, I'm sure you are, at least many of you are, but maybe not the other way around, because we usually don't talk about the energy much in the English system, so you probably haven't come across that too much. By the way, I heard somebody say slugs. No, what's the slug? Mass, right? It's the unit for mass. And the pound is the unit for the force. All right, well, like I said, this is about where we left off, because here was the goal. The goal was to put Newton's second law up here. So I will put Newton's second law, as you are already familiar with, in terms of linear motion. And it simply said this: add up all the forces on an object, divide it by its mass, and that will give you its acceleration. So what do you think Newton's second law would be saying when it comes to rotation, which we had half of it on the board already? It would be what? Yeah, net torque. That is the sum of all the torques. Divided by? Yeah, it's moments of inertia. Not its mass, but its rotational inertia would give it its angular acceleration. And so I'll finish this middle piece, which was already on your chart before here. But this is that, what is the moment of inertia? And so that's what we spent Wednesday on, doing a lot of calculations and trying to get you to understand the moments of inertia here. And so here's this idea of torque. And so the two together, the torque, the moment of inertia, is Newton's second law. And so you'll see that as we do some examples here. What is the acceleration of it? Watch. This was the one. Again, we kind of saw this already, but it's worth seeing it again. If I take this contraption right here and I let it go, I have a certain angular acceleration. But if I wind it back up, well, actually before I wind it up, I'll do this first. This is what I did last time first. So look again. Here is the angular acceleration. It's pretty fast. If I wind it back up and put these 4 masses on here, 4 kilograms, and let it go, can you tell it's a little lower angular acceleration, a little more sluggish? And if I were to ask you why, you would say because? Okay, I put more mass on it, which resulted in more moment of inertia. Yeah, more rotational inertia. Okay, fair enough. Then, if I take these masses and I move them further out and let it go, you would say, oh yeah, that has a less angular acceleration. Why? Okay, again, more rotational inertia. And in this case, it has more rotational inertia because the mass is further out in position. Not that we have more mass, but it's further out in position. And then the final step, if I were to take this string and wrap it around a different pulley, this happens to be the bottom pulley now, instead of that top pulley. And that's probably enough to illustrate it. And then let it go. You will hopefully notice one last step. Isn't the angular acceleration even less now? And why? Less torque here. And so Newton's second law is right here. And so you saw me twice increase this, so I got less of this. And then finally this last time is I lessened the torque and then lessened the angular acceleration. And so that was this little rotating stage, which, by the way, the one you have in lab today looks similar to that. Fortunately, it's got less friction than that, so you can measure things a little better, and it's professionally designed and built. And so unfortunately it doesn't have as many pulleys. So I like this one in the classroom. But and it's bigger that you guys can see it well, but the one in the lab is a lot more accurate. So more on that in a minute there. Well, like I said, just a couple other little things here and we'll be done with the chapter. The next last thing here to do is to talk about work. Well, didn't we say work was what? Okay, I heard force times distance, but it is more complicated than that, isn't it? Well, okay, it's also changing kinetic energy. I'll go with that. But just the fundamental definition of work. Yeah, it is force times distance, but it's really how much force, right? So it's the component of the force in the distance that it moves. And now it's more than that, because what if the force changes? Then you have to integrate it. So what we had was this. We had an F dot dr. The dot product gave us how much of the component of the force is in the direction of the movement, and then the integral added up all of those little movements to get us our total work. And so that was our work. So with that in mind, what if we have something that is not translating, or a linear motion, but something that is rotating? How do you think you're going to calculate the work there? Work equals? Oh, good. So it's still an integral, and instead of force you have torque, and instead of distance you have angle. Good. Angle, right? And so it's torque rotated through an angle, because in place of position we have angle, and in place of force we have torque. I suppose you could also put a dot product here, but remember in this chapter we kept ourselves to a single axis of rotation. So we don't have to worry about like the force has multiple directions, an X component and a Y component. We don't have any of that. So I'm not going to even bother to put a dot product there. I think that will confuse you more than it will help you. So we'll just leave it off. In the future that will change for you. But the future not being this semester, this class, and maybe not even this school. I should probably look at what our dynamics class does, but I bet our dynamics class doesn't even worry about multiple axis rotations. That's an upper division issue that you'll do when you guys transfer, which probably will be in 2 years. Although, anybody transferring? Anybody trying to transfer? No, there was a few you talked to me. Yeah, that you're filling in your applications and you want to transfer before you finish our sequence here. But anyways, you'd still have to finish your sequence when you get there. So it'll be a couple of years before you see that. Somebody said this one, change in kinetic energy. Okay, that's fine. That's the work energy theorem. That's true. And I would say the work energy theorem still exists. It's just our kinetic energy would be calculated with the angular speed instead of the linear speed. So we still have that. And I wasn't going to put that there. I'm kind of hoping that was an obvious step. But we had that on the last chart where the kinetic energy is 1/2 I omega squared. So yes, that's still true. The work energy theorem, that the work you do does result in a change in kinetic energy. And the last thing before we then move on to example problems is power. We used capital P for power. If you remember, we were doing linear motion. This must have been chapter 7 or 8. What was our definition of power? Okay, work per time. Okay, that's not going to change. It's still work per time. But when we put work together with force, what we had is F dot dr with time, and if you remember, then we put the dr with the dt and made it a force times velocity. So power became force times velocity. So what do you think it would be equivalent to when we get to rotation? Torque times angular speed, right? So we still have speed, but just now it's angular speed, and instead of force we have torque. And so, sure enough, wanted to put those on the board, part to just kind of review what you did a while ago, and hopefully that will sink in. That's one thing I like about this chapter. I told you, this chapter can be either easy for people or hard for people. And I've noticed it tends to be easy for people when they see the analogy. That's why I've spent this whole time saying, do you see the analogy between the linear motion and the rotational motion? Because it's a long chapter. And we don't spend much time doing these things, because the idea is, hey, think about how you would have done this problem when it was linear motion, and so now do it again for rotation. And I can't keep overly emphasizing that. That is the idea. That's the strategy you want to set up. And when you see that, then the chapter doesn't look so overwhelming. It's not like it's 8 new chapters. It's just a repeat of those 8 chapters. And so when you see it that way, all that old stuff, then you're just kind of repeating a second time. And so that's why I like this chapter. It makes the chapter easy, and it lets you review as you are starting to do things for the second time. And the first time it might have been hard, and now the second time it's like, okay, makes more sense. I wish I would have saw that when I took the test. I would have got a better score. But now I see it. So now in the final I'll get it right, type thing. And that's what I wanted to point out. Well, like I said, just a few things. There's one last thing the author has. He does this. He says, let's think about something now rolling down a hill. And he says, what if you took something like a cart that has some wheels that do rotate, but most of the object does not rotate? Fair enough? So let's just say there was nothing rotating, and we're only using the wheels to avoid having any friction, okay? And so you can think of this as an object not rotating, but going down an incline without friction. Now, how would that compare to, say, a solid disk that you would put up here? which has the same mass as that, and it rolls down the hill. Or how would that compare to, say, a hoop that again has the same mass? This one happens to be made out of metal. But of course the difference between the disc and the hoop, as we worked out last time, is that the mass on a disc is spread out throughout the whole disc, whereas a hoop, it's all out at the rim. And then if you let that one go, and it rolls down the hill. Do all of these roll down the hill and have the same speed at the bottom? And if not, which one is fastest? And why would you say one is faster than the other? Yeah, so good. A lot of you are seeing it here, is that wouldn't you agree that if all the objects have the same mass and they start up here at the top, don't they all have the same gravitational potential energy? And so as they roll down the hill, don't they lose the same amount of gravitational potential energy? And then where does that energy go? And hopefully what you're seeing into this, it only goes into a linear kinetic energy. But these guys, it goes into a linear and a rotational. So the fact that you use some of your energy to make these things rotate tells me they're not translating as fast. And it's because of that, I would say that if I made these race, which one's going to win? Yeah. And I'll ask it again. Why the car? Okay, it's not rotating, meaning it doesn't have to use up its energy for rotation. And so, yep, sure enough, this one beats. Same logic here, right? Which one do you think is going to win down the hill? Yeah, same logic, right? Car's going to win. This one's going to go down and beat it. Because this one doesn't use any of its energy to rotate. And so if you understood that, then you probably understand this one. Which one wins? Or is it the same speed? Yeah, I hear a lot of you saying the solid one. Why? Okay, I would agree it's related to more of its mass to its center. Keep going with that. Less rotational inertia, good. Go with that. Meaning, in terms of energy, takes less energy to rotate this one, right? The energy has to do with its rotational inertia. This one is less. So this one is not going to consume, if you will, as much energy of that one in terms of rotation. So this one's got so much energy in rotation that it has very little translational energy. This one has a little bit of rotational kinetic, so it has a lot more translational. And so letting it go, sure enough, this one wins. And so this is my first example. It's not an example out of the book, but I thought it would be a good first example. Let's calculate the speed of each of these. Let's do the cart, let's do the disc, let's do the hoop. What would be the speed of each of them? All right, so let's start with the cart. How would I work out the cart at the bottom? How would I work out the disc at the bottom? And how would I work out the hoop or ring at the bottom? Well, we'll start here with the cart. In fact, maybe I'll put a generalized picture over here. Here is the cart, something like that. And it's going to roll down the hill. Well, the first thing to do is go back to, we're going to use energy, we're going to use forces to calculate this. Yeah, probably your best bet here is energy, so let's use the principle of conservation of energy. That's how we were doing it before. Even though we have things rotating, same logic. If your question is about speed and you know distance, which in this case we do, it's a height issue, focus on energy. Okay, so I'm going to attack this problem with conservation of energy, not Newton's second law. All right, now, as we learned about gravitational potential energy, where do you want to call y equal to 0? The ground? And I'm not opposed to that, but I do want you to remember what we did in chapter 9, didn't we? center of mass issue? And so it might make more sense, maybe not, to measure things from center of mass. And so when this thing gets down to table level, is its center of mass at the same height as the table? No. So I'm more tempted to say, look, why don't we think about this cart getting down to the bottom? There's its center of mass. Why don't we call the center of the mass of the cart y equal to 0? So in other words, does y equal to 0 equal the surface of the table? No. I like to put it where the center of mass is, because that's as low as it's going to get. The center of mass is not going to get as low as the table. And so what I can start with then is to say, okay, this is y equal to 0. And then likewise, I can say my initial height is, well, I'll just call it y initial. Just leave it alone. So I can do this in kind of symbols here. But there's my initial height. We could probably measure it and get some kind of number. But we'll just treat them all the same. So they all start with the same initial height. See, because what would the disk look like? Wouldn't the same logic be true down here at the, for the disk? Wouldn't it roll down the hill? And as it rolls down the hill, it'll look something like that on the table level? And its center of mass of this would be where? Yeah, the center of the object. And that's not the same height as the tabletop. So why don't I call its lowest point, where its center of mass is, let me call that y equal to 0. Because then when it sits on top of the hill, isn't that the initial height? At least slightly. We can say, there's a slight change because of the angle here. And the hoop, the same thing. In fact, I guess the picture for the hoop and the picture for the disc is a lot the same. Okay? Just one's solid and one's open. But either way, here's this idea that I would write this as mgy initial. Over here, I would give it initial energy of mgy initial. Over here, I'd write it as mgy initial. And so there would be my first step. How much energy do I start with? And in this case, it's only gravitational potential. There's no translational kinetic, no translational rotation, no springs that are compressed or stretched, nothing else going on here. So that's all the energy I start with. But here's where it gets kind of interesting here, and here's where it gets different, and this is why I'm doing this as my first example. Where does that energy go? So in the case of the cart, as it gets down to the bottom, it has no more gravitational potential energy. Where is its energy? It's all kinetic, 1/2 mv squared. And it's all translational kinetic. That's all this object is doing. Ignoring the fact that the wheels are going around there. But like I said, small wheels, light wheels, we're kind of ignoring that. But over here, what would I say here about the disk? Yeah, does it have a translational kinetic energy? Yes, and a rotation. And so that's the new piece for this chapter. That as we were working out our conservation of energy principle, we would use all of our other energies that we learned before, add one to that for our rotation. And then that same thing for the hoop here. And so this would be a 1/2 mv squared plus a 1/2 I omega squared. Now wait, I should go further here. Any heat? Is there any friction here? And those are two questions, separate questions that I hope you caught. I'll start with the first one, any friction. And then the second one, any heat. See, something interesting is happening that we didn't see before. Let me start over here with the cart. Any friction? Yeah, let's not worry about the wheels. I mean, the whole idea of the wheels were to say, look, treat it as if it was frictionless. That's why I put it on the wheels, blah, 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 blah. Not perfect, but I just wanted you to treat it here as no heat. So can I put plus 0 where Q equals to 0? There is no friction. Because here's really what I wanted you to think about, is this object that's rotating. Plus what? Is there any friction here? Yeah, there has to be. If there was no friction, what would happen here? Yeah, this would start here and just go there. Isn't it the friction then that is making it rotate? So a free body diagram, I guess, would look something like this. The contact from the incline would be right about there. And if we take the center of the object to be its center of mass, there would be a force of gravity, mg. There would be a normal force from the incline. And there would or would not, I guess that's kind of the question, be a frictional force. Let's look at the force of gravity and the normal for a moment. Those forces are there, agreed? How much torque do you get from each of those? How much torque? How do you calculate torque again? Oh, I guess I never put it on here. RF. Let's look at this. And of course, I guess to define torque, I have to say torque about what axis, just like we emphasized moment of inertia about what axis. But I'm talking about the center. So the rotation about its center. How much torque do you get from the force of gravity? Would you agree the force of gravity is mg? But it's really this. What's this? What's R for this case? Do you see it? Okay, so it's the distance from the applied force to the center of mass. And what is that in this case? Is it the radius of it? Where is the force of gravity acting on this disk? At its center, its center of mass. So how far is it from its center to its center? 0. So how much torque do you get from gravity here? 0. That's why I'm trying to say this object does not rotate because of gravity. If you were to put a nail through this and just hold it out here, does that make it rotate? No. Force of gravity gives you no torque. It gives you a force, but a torque? No. It would be like back on this picture. What if I came over here for this wrench and I said, all right, I'm going to take this wrench and I am going to turn this bolt. So what I'm going to do is I am going to push right there. I'm going to grab the bolt and just push right at the center of the bolt. Is that going to give me any torque? No. Is that going to make it rotate? No. And that's what I want you to see here. And that's what it, like I said, makes this a tougher chapter. It is connecting that whole idea of what really is torque. And yet I have a force, but I don't have a torque. Anything right through the center means that, yeah, you can have all the force you want, but if you're pushing it right at its axis, that's not going to make it turn. It's no different than if I came back up here and I knocked these weights off and said, okay, I want to make this wheel turn. If I take my finger and I put it right on the center and push, that doesn't make it turn. I got to push over here or over here. That makes it turn. I need a distance. No distance, no turning, no torque. And that's what I have here. And that's what I want to make sure you saw here, because this isn't so obvious here. So that first step here is, as I draw that free body diagram, I would say, yes, I have a force, but I have no torque. So force of gravity, not making it turn. How about the normal force? Isn't it really kind of the same thing? I mean, maybe a little different, because you could say that the normal force is actually acting out at the rim. I mean, isn't it making contact at the rim? So in this case, I would say there is a distance. The distance is the radius of the ring. But here, what about the angle is the key? Yeah, the angle is either 0 or 180, depending on how you want to look at this. But that still comes out to be 0 torque. That would be, again, like coming over here. Instead of pushing at the center, what I'll do is I'll push at the rim. But I'm putting straight in towards the center. And so I can push all I want straight towards the center. It doesn't make it rotate. It only makes it translate. Right? And so this is not going to make it rotate. I need an angle like that. That'll make it rotate. So again, rotations are much more complicated. I might even remember telling you guys in 102, and it said, okay, we're going to do one chapter on rotation. It's the hardest one of the mechanics. Then we'll move on. We'll save the other harder stuff till we get into Physics 121. Here we are here. Okay, and so we're going to look at this rotational stuff here. And so again, no torque from the normal, no torque from gravity. What is the only thing that makes this thing rotate? Right there. The friction. If you were to say, what is the sum of the torques? You would have a 0 from gravity and a 0 from the normal force. Now, from the friction, that's not the case. The friction would be a distance of r, if this r is the radius of it, and the friction would be F, and the angle would be 90 degrees. So yes, you do get a torque from friction, and that's what started this whole conversation of what is making this object rotate. What's making it rotate is the force of friction. So I'll say it again. If there was no friction, I'd put it here and it would do what? This is what it would do without any friction. But it is the friction that is applying the torque that is making it turn, which results in the rotation. Fair enough? So maybe now I can ask this question. The second question, how much heat goes here? And maybe I should ask, what kind of friction is this? Is this a static friction or a kinetic friction? Good. Most of you saying static, which it should be. I know the object's moving, which can be tempting to call it kinetic, but we went through this back in chapter 5. It is not whether the object is moving or not. Is there any sliding going on? Is there any sliding? No, not in this case. We call this pure rolling, so be careful as you read the problems. If they say pure rolling, well, what they mean is point by point matches. There's no sliding between the surface and the rotational object. So this is not pure rolling or sliding. This is pure rolling. Okay? And so when they're talking about pure rolling, they mean no sliding. No sliding, of course, means that we would be using a static friction. And so when we come back to this whole idea of work or heat, since there's no sliding going on, how much heat is formed? Zero. So all that was a long conversation to say we could have ignored it and gotten lucky, but we'll only get lucky a few times, and we'll come back to bite us if we don't realize all the details that are going on in there. And so these are all the details. So I wanted you to see that after a long analysis, it is the frictional force that makes it rotate. We must have friction, but something different about the friction. The friction didn't turn into heat as we had in the past chapters where it was sliding down. Here, the friction showed up as a rotation. And so That's the nice thing about rotating. And I think you probably know that. If you had a big box sitting in the driveway and you had to move it, would you rather it be sliding as you push it or rolling on some wheels as you push it? Rolling, because what you're hopefully discovering here is even if you have some friction, the friction turns into a rolling effect, a help in sense of rolling along, even though there still is friction. So the wheels don't get rid of the friction, they just change the behavior of the result of that friction. All right, so same thing can be said about the hoop, that I'd put a 0 there. So answer, is there friction? Yes, it wouldn't rotate without it. That's where we get the torque. Normal force, gravity, no torque. But we don't have to worry about any calculation in terms of heat either. So that's kind of nice here. So pure rolling results in there. All right, so now if I go through my math, you'll see what begins to happen. The m's cancel off. If I bring the 2 to the other side, you'll see an equation that hopefully is not a surprise. It's the same equation that we did back in chapter 5. An object going down the hill has this speed. All right. But what was interesting in chapter 5, without any rolling, is this turned out to be the same speed for any object. Did you see here it doesn't matter what the mass is? Doesn't matter what the shape of the object is? If it goes down that hill without friction, it's going the same speed. Whether this be a big object or a small object, a round object or a square object. Its shape, its mass, it didn't matter. More mass means it started with more energy, but it needed more energy to get going at that speed. And so that was nice. It doesn't happen here anymore. As you just saw me do a few moments ago, rolling them down the hill, did they all end up at the same speed at the bottom of the hill? No. And so let's go through that math here. And so what is its speed here? Well, maybe I'll start with mgy initial 1/2 mv squared. And what I'll do is I will look at this omega, because I claim that there is a connection between the rotational speed and the linear speed. I think we did it last Monday. And remember what it is? If we had something spinning at an angular speed omega, what was the speed at the point on the rim? Well, you had to multiply by its radius. So if its radius is r, that would be the mathematical connection. That's convenient because then what I get is a 1/2 an m plus a 1/2 I r squared, and then there's my v squared. So you can see the math is coming out a bit different than for the cart because of that extra term. Let me factor out an m. Now you may say there's not an m in this equation, but I could certainly write it like this, and that will be useful as we try to compare what if I have something rolling compared to what we had before we got to this chapter without letting our objects roll. And so obviously we're getting more sophisticated. We're getting to more realistic problems. We're letting them roll. But the reason I say all that is because this would let an m show up on both sides, and I can cross it out and then ask this question. Yes, it's rolling, so no, it's not going to have the same speed as something over here, but this disk that is rolling, does it matter how much mass it has? No. And so this disk could have been cut in half and had half as much mass. It could have been a solid lead disk. It wouldn't matter how much mass it has. The fact that it has more mass to begin with means it has more energy, yes, but it also needs more energy to go at that speed. And so just like we saw over here, that the mass didn't matter, anything that ends up at the bottom of the hill is going the same speed, I would say the same thing. Any disk, regardless of what its mass is going to end up with the same speed down at the bottom of the hill. In fact, let me do a little bit more math, because I think a couple other things come out a little bit surprising. I'll bring the 2 to the other side, so this will be a 2, a g, and a y. And so I end up with a 1 plus I over mr squared, v squared. I'll just then solve this for v, and I get a 2gy, and I guess this is initial y, over 1 plus I mr squared square root. And now I can begin to see, is this speed the same as that speed? Oh no. And which one is bigger? Well, this one is clearly bigger because what we have in the numerator is the same. That's why I kind of set it up this way so you can compare the two. And so clearly this one is faster. You even watch me roll them down the hill. So yeah, we know that one's going to win. But it's 1 plus a little bit. You see, it's this little bit that is the difference over here. This just has a 1 downstairs. This has a 1 plus a little bit, or maybe even a lot. All depends on I and m and r squared. Or at least it appears to be that way. Watch, let me keep going. And so I've got a v equals square root. I've got a 2, a g, a y, and a 1, and a plus. Now let's go to the I. What is the moment of inertia of a disk? Do you remember working this one out? What was it? Close. Or maybe I didn't hear you. 1/2 mr squared. So this will come out to be a 1/2, an m, and an r squared. And that's why I wrote it as an mr squared. I don't think it was so obvious till you make this step here. But watch what cancels off. Doesn't the m cancel off? And maybe I actually already said that. Maybe I said it prematurely, that the m canceled off here, but I guess it was still buried in there. But now it cancels off completely. So now my statement is, I should make it, that it doesn't matter what the mass of this disk is, any disk of any mass of this size will be going the same speed. But I would even say, physically, the size doesn't matter. The r's cancel off. And so this could have been a disk that was this big, or could have been a disk of this big, but the fact that you have different r's doesn't matter. The speed at the bottom of the hill becomes the same. And you can kind of see that in the sense that if r gets bigger, two things happen. One, don't you get more torque? Even for the same weight, the same mass, don't you get more torque? Isn't torque having to do with the radius of it? So that if I make a bigger disk, I'm going to get more torque. But at the same time, if I get more torque, don't I also get more rotational inertia? So yes, I get more torque, but it's also harder to rotate that object. So the two balance each other. And so just like they did back here, just like more mass needed more, gave you more energy, but you needed more energy. Same thing here, more mass meant you got more energy, but you needed more energy. Bigger R means you get more torque, but you need more torque also. So the two balance each other out. So it's kind of neat here that it doesn't matter what disk is placed here. A lot of mass, a little mass, a big radius, a small radius. They all end up with the same speed down the hill. And that speed would be smaller than this speed. So its shape does matter. But all disks would have that same speed here. And it looks like it's a 4/3 G. And so you can see that the 4/3 under the radical is smaller than the 2 that is under the radical. And so sure enough, that disk is going to get down the hill and its speed would be less. I can do the same thing again now for the hoop. And it looks like some of my math carried over a little too far to under that category there. Maybe I shouldn't even go through all that math. Wouldn't the math all be the same until I did the substitution of what is the rotational inertia of it? So let me do this without repeating all that math. Let me just put square root of 2gy initial divided by 1 plus I over mr squared. So nothing would change as we do the hoop up to this point. What would change is now at this point when I ask you, what is the moment of inertia of a hoop about its center? Answer? Yeah, you can look at your notes from Wednesday. You can look at the book, the big table.
R squared half.
Yeah, mr squared, yeah. So it doesn't have the half in front. And you might remember, we did that one first. That was the easy one. We did the hoop, and then a bunch of hoops made the disc. The disc was the hard one, but the hoop was the easy one. And again, same logic. It's worth saying it again here, but notice the m's cancel off. So any hoop that I place up here, regardless of its mass, is going to have the same speed, and regardless of its radius. Same thing. More mass means, yes, you start with more energy, but you need more energy to be moving. Radius? Doesn't matter. Bigger radius, yes, gives you more torque, but yes, you need more torque to get that larger rotational inertia of an object to rotate. So they cancel each other off here. And so that becomes a 1 plus a 1, which is a 2, and a 2 cancels with a 2, and so you just get, and maybe I'll just put a 1 here so we can see, but there's a 1 here, there's a 4/3 here, and there is a 2 here. So each object with its different shape, even though its mass and its radius wouldn't matter, its different shapes do, and they all go at a different speed. And you can see then that this number is the smallest, and you saw me race them. This one lost. This was the slowest one. The disc clearly beat the hoop, and likewise the cart clearly beat the disc. And so there's our rotating objects. And that's what I wanted you to see as a first example. It makes a really good first example, even though it might be a little more sophisticated because it's an energy one and it's not a kinematics one. And I debated this with myself. I said, ooh, which one do I want to do first? Because I think kinematic problems are the easier ones, and so, you know, I'm going to jump back to those now, but I did want to take a close look at an object rolling down a hill and using conservation of energy. But I'm hoping you saw this. You saw that the question says, what's the speed at the bottom of the hill? Had this been just a linear motion of an object going down, you would have used conservation of energy. So use it again. Add up all your energies. The only thing that's new is we've added a small piece right here to our conservation of energy. Right here. Of course, now we have to get it for that object. And so we got to look closely at our object. All right? Well, let me, like I said, spend the balance of the time today then doing a bunch of examples and seeing if these kind of make sense for you, particularly one coming up in a few steps, number 49, because that's almost an identical copy of what you're going to do in the lab today. And if you haven't spent much time in this chapter yet, this lab could hit you kind of hard. So I do want to at least give you some pre-enlightenings to it, if you will. But number 4 is supposed to be a simple kinematics one. It's supposed to be an example like the one that you would have saw back in chapter 2. Well, let me just read it to you. Here it says a central fuse in a medical laboratory rotates at an angular speed of 3,600 revolutions per minute. It is then turned off. It rotates 50 more revolutions before coming to a stop. Find the constant angular acceleration of the central fuse. All right. Does this sound like a kinematics type of problem? Do you see it? I mean, we're talking about rotating instead of translating. But aren't they telling you the initial speed? Aren't they telling you how far it goes? 50 revolutions? Right? And so they are clearly, hopefully, setting you up for a central fuse. And it says, find the acceleration. They even do better than that. They say, find the constant acceleration. So is this a constant acceleration problem? Very clearly, right? So I can use those 4 kinematic equations. Now I'll just put one on the board because I think the first one gives it away. Final angular speed is equal to initial angular speed plus the angular acceleration multiplied by time. Oh no, maybe that's not the one I want. Because that one has time in it. Have they given me how much time it takes to come to a stop? No, they really gave me how much distance before it comes to a stop. So which was a better probably equation here? Do you remember number 3? Number 3 was relating to what is the final speed compared to the initial speed? And the angular acceleration, does that look familiar? So I think this one would be more appropriate. Not to say we can't do 2 steps to get this one, because remember, equation number 3 is number 1 combined with number 2. So we could have done my first equation, got time, put time into the second one. But that's what number 3 is. So I'm just going to jump right to equation number 3 and start filling it in. But did you catch that? Because if you don't see it, this is going to be a hard chapter for you. If you see it, it's an easy chapter. Do you see that I can just, what would I have done had this been a question about linear motion? What would I have done if they had told me the speed of the car is 3,600? It travels for 100 meters before coming to a stop. What is the constant acceleration of the car, right? I would have done exactly the same thing. So go back to your kinematics. Ask yourself what you would have done had this been a translational or a linear problem, and then say, what am I going to do? Exactly the same thing. All right, so let's fill it in now. What's the final speed? 0, right? How long before it comes to a stop? Right, same thing. If that car was moving in, how long before the car comes to a stop? Right? And so that was the key. They don't say the final speed is 0. That'd be too easy. That, you know, like I said before, that would be a 102 problem. That, you guys would be bored. You would hate to have a problem that easy. I'm sure of it, right? You just, too easy. What is that speed? What is the initial speed? Now, this one we want to be real careful with our units. Did you catch it? What did it say? 3,600 what? Revolutions per minute. Now, those are not the units we had when we talked about angular speed. What units did we use? Radians per second. Now, does not say you couldn't use these units, but this is one of those back to chapter 1. Watch your units. Watch your unit conversion. Don't get caught into the trap of mixing centimeters with meters or miles with kilometers. You know, pay attention to how they have it. And we've been doing radians per second. And so I'm not even going to ask you if you want me to change it. I'm going to change it. I mean, do you want to leave it in these new units and worry about the new units, or go back to what we've been talking about? And well, let's just go back to what we're talking about. So I'm going to write my first step as 3,600 revolutions per minute. But I'm not going to stop there. How do I change it to radians per second? Well, maybe I'll start with the minutes. How do I get minutes into seconds? Yeah, well, 1 minute is 60 seconds. Okay, so that's going to get rid of my minutes. And like we did way back in chapter 1, my unit conversion. Multiply by the number 1. That doesn't change anything, except changes the units for you. So now I would have revolutions per second. And I want radians. So what's the other thing I need to do? Now, remember that 2 pi radians is 1 revolution. So that's what I need to do first here. And that would convert them, this angular speed, into a radians per second from a revolutions per minute. Then I've got the 2. Now I'm going to solve for alpha. And so now here's the angle that it moves. And if you were looking ahead, this is why, and they gave us in revolutions, so we probably could have done this and maybe even appreciated if we didn't convert back to those other units, because they gave me things in revolutions all the way through. But I just felt, hey, let's cover both of these here as an example. But how far did it go? Well, it says it takes 50 revolutions before it comes to a stop. So this would be 50 revolutions, but 2 pi radians are in 1 revolution. And so that's going to convert my revolutions into radians. So when I solve all of this, I am going to get radians per second squared, as opposed to if I didn't, I would have revolutions per second squared. And then I'd have to watch my minutes, and stuff. And I could get it in revolutions per minute squared, which doesn't sound real inviting. But this would be my conversion here. So I'll take this one. So as you said, this top one is 3600. Across the top would be times 2 times pi. Across the bottom would be 60. And so that's about 377 radians per second there. I'll square that and hit equals. Okay. Move it to this side, so it's now negative. Divide it by my 2. And divide it by my 50 times 2 times pi, and then close parentheses. And so if I've done all my math right, I get a negative, and I get 226. So a negative 226 radians per second squared is the acceleration. What does the negative mean? Okay, does negative always mean slowing down? Not exactly. It was probably a better way of saying it. It means what? Yeah, it means it's opposite of the direction it is moving. I picked the direction it's moving as positive. So I chose that right here. I said, let's call its initial speed positive. And once I did that, then my acceleration should come out to be negative. Had I chosen this to be a negative number, then this would have been coming out to be a positive. So it's not so much that the positive and negative is as important. What's important is that this be the opposite sign of that. Now, the tradition is, and I should do it again here, if you were looking at something rotating and it's rotating counterclockwise, that traditionally is called a positive rotation. And clockwise is traditionally a negative. And I say traditionally because can't we change the tradition? Didn't we do that with the x-axis? And so we could have. And this problem didn't even say clockwise or counterclockwise. So I just picked it, whatever direction it is, positive. So I'm mentally in my mind, if I'm sticking to a traditional one, thinking of it as something spinning in a counterclockwise direction. And then slows down, slows down, slows down, slows down, stops. Okay? But again, it's a good, at least I think it's a good first kinematics one. And it's certainly much easier than this one over here, as all of our kinematics ones were in general much easier. And that's what we did first. We did some kinematics. Then, if you recall back on last Monday, after we did some kinematics, we did this step. So let's do a number 35. Number 35 is a good problem where it asks you to think about things both in terms of its rotational motion and in terms of its translational motion, or its linear motion, your author calls here. And so what's going on here? Look, well, let me read the problem here if you don't have the book here, which I know sometimes it's kind of heavy to carry this, but if you do, you get an extra unit of PE. Did I tell you that before? So you carry your book every day, and you'll get an extra PE unit. Model airplane with mass of 0.75 kilograms is tethered by a wire so that it flies in a circle of radius 30 meters. The airplane engine provides a net thrust of 0.8 newtons perpendicular to the tethered wire. A. But let me just draw what I've read so far. Okay, so here's what I have. I've got, and I'll take an aerial shot, so a top view looking down. Here is the tethered wire over here. Here then is this airplane. So maybe this airplane looks something like that here. And as we look on it from above, it's making this circle. The problem goes on to say it has a net thrust of 0.8. And I guess what they mean probably by that is there would probably be some air resistance as this airplane is moving through the air, which was our chapter 6 discussion, but I don't think the author wants us to get, too bogged down in that. He just says, look, let's just look at then the thrust and net thrust, and I don't know what that is, but I know the two together have to be 0.8 newtons. That's what he's trying to say here. So yes, the engine's probably, got something greater than 0.8, 1.0, 1.5, who knows? We don't know how much air resistance we have there. But the two together is a net thrust. So catch that in the wording, otherwise you might make it a harder problem then. But it is then accelerating, if you will, as it goes around here. And that's what he wants to work on here. So model airplane, mass, I should put that up here, 0.75 kilograms, is then going around in a circle with a radius of 30 meters. It is tethered in such a way that, it makes a radius of 30 meters, and the engine, or the net thrust here, is 0.8 newtons. And it's perpendicular to the wire. A, find the torque that this net thrust produces about the center of the circle. All right, so that gives us our first calculation for thrust. Here is torque sine of theta. All right, so what's R in this case? Okay, 30 meters. What is F in this case? Okay, 0.8. What is the angle in this case? Is it 90? What's the angle again? What was the definition of the angle? Yeah, good. So the angle is between the force and the distance arm. So it is 90 degrees, good. Which is, as we talked about, what you would want if you want something to have a maximum amount of torque. You want to be pushing it at 90 degrees. Okay, so that's the sine of 1. And 8 times 3 is 24, so this must be 24 Newton meters, right? And so there's the number, 24. There's the units, Newton meter. And so there's our first calculation on doing a torque. All right. B, find the angular acceleration of the airplane when it is in level flight. So this is just level flight, going around. What is the angular acceleration? Well, this is our first Newton's second law calculation here. Right? Newton's second law says that the angular acceleration is net torque divided by its moment of inertia. Now, I'm sure that's why we just did A. What is the net torque? Well, the net torque is what was resulting from here, from these net forces. So we have both a thrust and an air resistance. The author put them together for us, and we come up with then a torque of 24 newtons per meter. This brings us back to then rotational inertia. What's the rotational inertia? Then we spent all day Wednesday doing calculations. But this is the easy one. This is the very first one. Didn't we have I just equaling the sum of MI/RI squared, which in this case I equals from 1 to 1. There's just one object. It's that airplane. And I'm sure that's why he picked 30 meters. What he's trying to say here is, look, I know the airplane has size, and you might even say part of this wing is closer than that wing. So I wouldn't say all the parts of the wing are 30 meters away, but some of it is a hair less than 30 meters. Some of it is more than 30 meters. So it's not the hard calculation where the meter stick one, where some of the points are close and some of them are far. These are all roughly the same distance away. So you're gonna like this one. I mean, how do you get the moment of inertia of this one? Yeah, it's just 0.75 kilograms times 30 meters squared. All the mass is at 30 meters. So that was much easier than some of those hard ones we did on, excuse me, on Wednesdays. And rightfully so. I wanted, that was not what this was about. Wednesday's lecture was about that. Wednesday's lecture was about calculating moments of inertia of some of the harder ones. But this is just find a use Newton's second law here. So this becomes 0.75 kilograms, and this becomes 30 meters squared. And so now I'm going to get my calculator out here and say, all right, so there it is. So there's the 24. Divide it by 0.75 and divide that by 30 squared. And again, if I've done my math right, it's 0.035, and I'll round it to a 6. What are the units? Well, you're right. They should be radians per second squared. Let's check it. Is that what it comes out to be? Well, here's my Newton. And a Newton, if you remember, is a kilogram meter per second squared. So when I multiply it by that other meter, I get that. Then I have this kilogram meters squared. So kilogram cancels with kilogram, good. Meters squared cancels with meters squared, good. So I'm left with 1 over second squared. Is that radians per second squared? Yeah, it is. Same thing. Why? Because radian's not a real unit, and that's what we said last Monday. So yes, this does come out to be 0.0356 radians per second squared. Ta-da! Okay, so there's our first calculation using Newton's second law. So we got our first calculation of torque, Newton's second law, kinematics, and like I said, I wish I could spend a lot more time doing more than one example from each area. We did an energy one, and we'll do some other ones here, but are you catching what I've done? I'm going back to say, what did I do for translational motion? And once I see what I would have done with translational motion, I'm just going to apply that same thing to rotation. And then when you see that, then this chapter really becomes pretty easy, not so daunting. It's like, oh yeah, I see why it's long, because we're doing everything again, but I've already done this. And so this just becomes a nice review, at least in theory. And so that's the idea. I guess if you didn't learn it the first time, it becomes doubly hard, because it's like, I didn't get it the first time, and I'm not getting it the second time. I don't have the analogy to move forward. I think there's a part C to this one. Part C says, find the translational or linear acceleration of the airplane tangential to its flight. Okay, so now they really want us to find A. Not alpha, but A. But this is that part where we said, if you know alpha, don't you also know it's connected to A? Wasn't the translational acceleration r times the angular acceleration? And so its radius is 30 meters, and its angular acceleration is what we just did in part B, and so it's 0.356 radians per second squared. And so now I'll just take that answer I just got and multiply it by a distance of 30 and come up with a 1.07. And watch my units here. I'll put meters per second squared and just drop off the radians. The same thing. It's not a real unit. Add it, take it out, depending on what you need to do with it to make it clear. And it's not a real unit. It's kind of a clarification point there. But that would be then the acceleration of it. And those were our connections between the rotational speed and the angular speeds, or acceleration, I should say, quantities. All right, well, those are making sense. Let's keep going, or even if they're not making sense, let's keep going here till they start to make some sense here. 47 is next on my list here. 47 is a good one. That, again, I'm hoping you will see first things and foremost is read it, see what type of problem is. Is it a conservation of energy? Is it a Newton's law? Does it have, what kind of friction does it have? I mean, everything you would have done for translation. See that and then apply it to the rotation. Slight modification. Look at this one, 47. An object with a weight of 50 newtons is attached to the free end of a light string that is wrapped around a reel of radius 0.25 and of mass 3 kilograms. The reel is a solid disc. It is free to rotate around a vertical plane about a horizontal axis passing through its center. Wow, that was a lot of words. Did that make any sense to you? Did you get a picture in all of that? All right, let's go back to the beginning. An object with weight 50 newtons. All right, I got that much. All right, so here's an object. 50 newtons is pulling down on it because of gravity. mg. All right, so there's that first part. An object of weight 50 newtons. It is attached to the free end of a light string. All right, so there's a string attached. All right, so I'll put a little string. Here's a string, okay. It's attached to it. Light string, what are they saying there? Yeah, don't worry about the mass or the acceleration of this string. It's the objects that is going to be relevant. Okay. It's wrapped around the, oh wait. Object 50 newtons is attached to the free end of a light string wrapped around a reel of radius 0.25 meters and of mass 3 kilograms. Okay, so I got a reel this thing is going around. So this is the reel. It's got a radius of 0.25. It's got a mass of 3 kilograms. The string goes up, wraps around it. Well, that's what that part was saying. The reel is a solid disc. Okay, so it looks like this one here. And does it matter if it looks like this one or this one? Oh, absolutely, right? It's been the whole discussion. Okay, so it's going to look like this one. So, like that. Okay. Where'd it go? The reel is a solid disc. It is free to rotate in a vertical plane about a horizontal axis through its center. Now what does that mean? Vertical plane, horizontal axis, center. That make sense? So those are those 3 P's. Vertical plane, horizontal axis, at its center. So they're saying something like this. This is what this looks like. Here's the reel. I won't, so I don't mess up my picture, but you can do that. Okay? And so basically I got a string wrapped around it with small weight. Okay? And that's step 1. Got a good physical picture of what they're trying to explain here. And sometimes they give us a picture and sometimes they don't, and this one they didn't. Some of the other ones here next, they do. In fact, that kind of reminds me then, as long as I'm thinking about the picture so you can see the picture. I'm going to turn on the power to the overhead here. So the next one, I'll need to show you the image because this looks very much like the one you have in lab. And there's a lot of complicated pieces and I want you to see it. Very three-dimensional. And I don't think it looks as good in the picture here. All right, so vertical axis, rotating around. I'm sorry, horizontal axis, vertical plane, horizontal axis passing through its center. Okay, the suspended object is now released 6 meters above the floor. The floor. 6 meters. 6 meters above the floor. A. Determine the tension in the string, the acceleration of the object, and the speed of the object when it hits the floor. B. Verify your last answer, that is the speed of it, by using conservation of energy principles. Let's start with that first question A. Determine the tension in the string and the acceleration. Do I do this by conservation of energy? No. Why not? That's not what conservation energy gives me, right? Conservation of energy gives me speed at the end, yes. which is the third part of that question A. What's the speed? That's why part B is saying use conservation of energy to prove that. But to get acceleration and to get tensions, we need forces. This is a Newton's second law problem. Do you see that? You got to see that to know where to begin these problems. Like I said, we've now gotten way into this semester, and we got to start asking ourselves, what fundamental principle do I use? And really, this is just the beginning, because anything we do this semester is all mechanics. And so by the time we're into the third semester of this class, it's much more complicated. It's like, ooh, do I use mechanics? Do I use thermodynamics? Do I use optics? Do I do all of the above in order to solve this? So our library is building and getting more and more information. But this is what we need to notice. This is a Newton's second law. This is a free body diagram here, okay, to find the tension. So that's what I'm going to do first. I'm going to go free body diagram. That's what I would have done if this had been a translational problem and they asked for things like what is the tension and what is the acceleration. I would have drawn the free body diagram for the two objects. So let me do that here. Don't change any of that. But the key is to recognize that it is that same type of problem. It's a Newton's second law problem, and it is a free body diagram. So let me do the free body diagram for both objects. And in fact, the first object will be the one that we've done so many times back in chapter 5 that I don't think there'll be anything new here, but it's the new one, the one that rotates, that I do want to make sure you see here. But as I draw the free body diagram, I would say it's being pulled down with a force of 50 newtons. And that was given in the problem. It's being pulled up with a tension of T, and that is part of the question. What is the tension in that cord? I think that wasn't it tension and acceleration? Yeah, what is the tension, what is the acceleration, what is the speed? So there's my free body diagram for here. Now what I really want you to see is this then. What is the free body diagram for this rotational object? This this thing here. All right, so what forces are on this? Okay, somebody said its weight. I agree. There's its weight. But here's what's an important step here. And maybe I'll put a capital M for this one. So the little object will be a little m, and my big object will be a capital M there, okay? So here's a little m, and here's a capital M. But I really have to know where is that force. Because in order to calculate torque, don't we need to know the distance away? So that's why we did chapter 9. This is the force from gravity. It's equivalent to acting where? Center of mass, at its center. Keep that in mind, but that's why I'll draw the picture with a dot with the arrow coming from the dot. What other forces are on this? Okay, I would say the rope or string here is pulling on it, so I'll put a T there for tension. Good. Any others? Okay, needs to be fastened to something, fair enough. So where's that? Okay, so there's probably like a nail or something through this piece of wood, or maybe something more sophisticated with an axis and bearings. But somewhere along the line, there is the bearings, the axis, the nail pushing upward, right? And so it's probably made out of a solid material. Maybe I'll still label it as an N, like we would have done if it was sitting on a horizontal surface there. But where is it acting on the reel? Isn't it at its center? Okay, because how much torque am I going to get from that force? 0. And so can you see in this free body diagram 0 torque from this one? This does not make it rotate. How much torque do you get from gravity? 0. The only thing making it rotate is the torque from that string. And so this is like the rolling down the hill that we spent, 10 minutes analyzing. It's like, look, are there forces there? Yes. And what's happening here is there are two forces pulling it down and one pushing it up. That's for the translational motion. And I don't even think that's going to be even needed or relevant. I'll write it down, but I think what's going to be really relevant is the fact that it rotates. There's only one here that's needed for that, and that's the torque, the tension in that string. Okay? Well, so I'll come over to here. And so if I do my free body diagram, and will it be okay if I call down positive, just so I don't have to do negative numbers? I know this isn't the convention, but if I call down positive, look at the rotation. Which way is the rotation? Clockwise. And traditionally we call that negative too. So do you want me to call both of these together negative, or can I go ahead and call both of them positive? Positive? I'm hoping you'll say that. I don't want to lose anybody along those, but let's just call down positive and clockwise positive. So I'll put a little sign here and say, okay, down is positive, and be consistent, I'll call down positive, but this one's also going to rotate, so I'll call clockwise positive like that there, and kind of indicate that. I'm gonna get away from the traditional way and just use positive numbers here. So we'll call down positive, clockwise positive, because when I do that over to here, and I say let's do the sum of the forces in the y direction, I've got a force of 50 pushing down, and now tension, which is up, is a negative number, right? Negative the tension, has to equal to mass times acceleration. Fair enough? And as I said, I hope this is obvious to you. This isn't new. There's nothing new here. This is Newton's second law, chapter 5 stuff, applied in the vertical motion. Down positive, up is negative, add up the two forces, set it equal to ma. And that's all I can do with this one. This one is just translating, it's not rotating. What's new is over here. So let's do this one. I could do the sum of the forces in the y direction for this one, but I gotta admit, it's probably pretty boring. There's really nothing of interest here. I would have an capital G pulling down, I would have a T pulling down, I would have a normal pulling up, and that object does not accelerate. So you add up all those forces, you get 0. And although that's true, it's really this new one. What does all the sum of all the torques have to equal? If all the sum of the forces have to equal ma, the sum of all the torques have to be I alpha. And so that's the new piece, right? The new piece is we've got translational issues and rotational issues. And I purposely picked this one because this one is only translation, we don't have to worry about rotation. This one is only rotation, we don't have to worry about translation. So kind of separated our two objects into the easiest problem I can think of. That'll soon change. And we'll have rotation and translation at the same time. But this is probably the easiest one we can set up. And as we already mentioned, as you go to add up all your torques, how much torque do you get from these two forces? None. So what's the torque from this one? Okay, I'll put it as an R, a T, and a sine of. Yeah, and so we need to come back to this. This is kind of nice about doing the lab. You'll notice something in the lab that will help you as you do these problems. You wrap a string around an object, pull on it. It always comes off tangential to the object. No matter how you angle it, it's always coming off tangential. So the strings are the easiest ones. So this is going to be 90 degrees equals to I alpha. And this is really what I wanted you to see. Although this one is true, I don't think we need it in any way. I'll leave it up there just in case we do need it. But I think it's these two equations that we need to solve for. Because the question here is, number one, what is the tension? And number two, what is the acceleration? And so those are the two pieces here. However, I do need to make one more step because that has an A and this has an alpha. Are they related? Is A related to alpha? They are. How? Right. And so my third equation here is alpha is equal to A divided by R. Now, I should probably be careful with that because that's not how we worked out that problem. When we worked out that problem, what we said is if you had something spinning, the acceleration of some point on the spinning object. We didn't say it was the acceleration of the object that was falling. So are you sure that this A here is the same as this A? Well, it can be if we let R be the total radius of this reel. Why? Well, if this has an angular acceleration of alpha, then it will make this point on the rim have an acceleration of a, because the point on the rim is at a distance of capital R. Fair enough? And then the point on the rim is the same point where the string is tied to. So then I would say the acceleration of the point on the rim is the same as the string. And then I would say the acceleration of the string is the same as the little weight hanging from it. Okay, so yes, I would say that this A is connected to this alpha if I use the whole radius of the reel. That may or may not always be the case in every problem. So don't just blindly put them in and hoping it works all the time. We go back to that whole idea of, sometimes our equations are a little simpler and we can plug and chug. These you can't. You just blindly plug and chug and you'll get caught and mixed up in a terrible set of equations that you'll say, oh, there's no solution here. You got to make sure you're reading them as you go along here. Okay? All right, so now I think I can begin to solve it. I can put in my numbers here. Maybe I'll start here with m. I can solve for m. They didn't give me that explicitly. It's back here. They did tell me that the 50 newtons is the mg. That is 9.8 divided by 50. And so this m is probably a 5. Maybe it rounds up to a 5.1 or something here. And so 50 divided by 9.8 is, 5.1. So here is my mass of 5.1 kilograms. So I would take this as my first equation. 50 minus t equals 5.1a. So there is one equation with the two unknowns I am looking for. Tension and acceleration. They're also looking for speed, but we'll work on that. But that's my first step. Then over here, I can do exactly the same thing. Let me put in what I know. I know the r, that's the radius of this reel, so that's 0.25. T is unknown. Sine of 90 degrees is 1. Ooh, what's this one? I. Moment of inertia of a reel. Do I know that one? Yeah. Didn't we learn it was 1/2 times its mass, which is now 3, times its radius squared, which is 0.25 squared. So there's the rotational inertia or moment of inertia of the reel. Alpha is what we said is over here. Our alpha is our A divided by our R. So again, this is my second equation with a tension and an acceleration. Fortunately, one of those cancels with one of those, as well as the second one here cancels with the second one here. And so this comes out to be T equals, looks like 1.5A. And fortunately, the math isn't real hard, and I didn't expect the math to come out hard. It was the physics. It was, can you set up the free body diagram? Can you write out all the forces? Can you solve this? And I'm hoping, again, that you see the connection here. Unfortunately, with time, we're only going to be able to do 1 or 2 examples for you. But you see, this is what we were doing in Chapter 5? Free body diagram? Free body diagram for a couple of objects. Set the equations and see how they're related to each other and solve. And you're going to see a lot of that again. If I put this over to here, I guess I would have 50 minus 1.5a equals 5.1a, which when I bring it to the other side, I guess that makes 6.6a is equal to a 50. And so I can answer this first part. Well, what is a? Well, I guess it's 50 divided by 6.6, coming up with 7.57 meters per second squared. Or 5.8, I guess it rounds up there. But that's the acceleration. And then, of course, once I know that, I can get the tension by taking the acceleration and multiplying it by 1.5 and get 11.4. So this is 11.4 newtons there. And so that's 2 of the 3 questions. The third one then is, what is the velocity of it? Well, hopefully that's not hard, because that's good. This, again, has nothing to do with rotation. This takes us all the way back to chapter 5. Don't we know the distance is 6 meters? Don't we know the acceleration is 7.57? So with that in mind, we can say it is equal to initial speed. Actually, I'll do the third kinematic equation as we saw before, because the third kinematic equation involves velocity, acceleration, and distance. So what I can do is I can put 0 speed and I can put the acceleration. So the acceleration is 7.57 and the distance is 6 meters. And now I can take the square root of all of that and get its speed here. So this is 2 times 7.57 times 6 equals, and take the square root of all of that. And we're looking at 9.53 meters per second then for the speed when it finally gets to the bottom. So that's the 3 steps that we are asked to do. But then the part B says, shouldn't you be able to get speed by just using energy? I mean, if this was a question just about speed, I would have said, what principle are you using? And you would have said, oh, energy for sure on that one, right? So let's give it a shot here. Let's see if we can get the same speed by using energy. And so I guess I would have done this. Part B, and I would have said, all right, what energies do I have here? Well, obviously I have gravitational potential energy, but I'm also going to have a translational kinetic and a rotational kinetic here, right? So like we did before, in the first step, where do you want to call y equal to 0? Center of mass of? Yeah, good, like we did on the test. Why don't we just call a reference for each object? See, this one, we might as well call y equals to 0 for the real. Does it go up or down? No, so it just starts at 0, finishes at 0. In other words, there's no discussion about the gravitational potential energy from the real. There is no change. It doesn't go up, doesn't go down. So let's call that y. The one that matters, though, is right here. Where do you want to call y equal to 0 for this one? Yeah, and I think it probably makes the most sense, as you guys pointed out, to call y equals to 0 at the center of mass right here at its lowest point, because then up here it's 6 meters high. Of course, it also begs this question back with the author. The author said it was 6 meters, but he didn't really specify. 6 meters as measured from where? The ground, center of mass, the ground to the bottom of it, center of mass to center of mass. And because he didn't say, and he said this was kind of a small object, I'm going to say that he's talking 6 meters center of mass to center of mass, which would also be the same as ground to bottom of weight. So whichever way you want to do it. In fact, I'll encourage you in the lab in a few moments to say, why don't you just measure from the ground to the bottom of the weight? Because that's going to be the same as center of mass to center of mass. Okay. All right, so when I come back over to here, I would say that this is mg 6 meters, where the m is the 5.1 kilograms, g is 9.8, and the 6 is the 6 meters. That is all of my gravitational potential energy. That's my total amount of starting energy. So 5.1 times 9.8 times 6 comes out to be about 300 joules. So there's my 300. Oh, I guess I could have done that with easier with 50, right? 50 times 6 is 300. But anyways, sometimes I guess we get lazy with a calculator. So we get so lost in the problems, we forget how easy our calculations are. What is 2 minus 1? 2. No, you would never do that. But anyways, I should have just gotten 50 times 6 and got 300. But nonetheless, glad to see that it still comes out after all that work to be 300. So it doesn't surprise me that it's 300. So the total energy is 300 here to get us started. Okay, so that's the total energy of this. And then my point here is, where does it go? And this is really what I want you to see. Where did it go? Good. I'm hearing both a translational and this is the new piece, a rotation. But it's not just rotation either, right? Because it's the two objects. And as its two objects are now moving, this one is moving in a translational, so it has some energy. This one is rotating, so it has some energy. And so those are your two pieces. So this one for the real and this one for the translational object. So this would be a 1/2 and this would be 5.1 v squared. And so that would be the equation for that smaller weight there, the lowercase m. This would be 1/2, ooh, what's I? Yeah, we already dealt with that, but I don't want you to forget it. That's what this whole idea here is. This would be the rotational inertia of the real. And so this is going to be a 1/2 times a 3 times a 0.25 squared. So that is the rotational inertia of the real. And then we have the omega. But I claim that that omega is related to that v again. It's kind of the same logic here. Isn't the omega equal to the linear speed divided by the r? Now again, I should emphasize, when we developed that equation last Monday, it was not the speed of an object that was hanging, but it is the same. It was the speed of a point out here. But if that point becomes the total radius, then that's the speed of the rim. And the speed of the rim is the same as the speed of the string, and the speed of the string is the same as the speed of the hanging weight. So in this case it works, but maybe not every case. This case, yes. So be careful with this, but this would be a v squared then over a 0.25 squared. And that's kind of nice because the 0.25 ends up canceling off here. And so I guess I get a 1/2 times a 5.1 for this term. And over here, I guess I get a 3 over 4. So there's a 3 over 4 and a v squared there. And so I should be able to solve this for v also and hopefully get the same number here. So I will do a 1/2 times a 5.1, add to it 3/4, take the 300 and divide by that number, and then take the square root of that and get 9.53. Does it match? Yes. Good. 9.53 meters per second then is the speed using conservation of energy. Okay? So, again, did you see that big picture at the beginning? What would I have done if this would have been translational motion? Okay? And maybe this would help you if you were still kind of shaky or iffy about translational motion. This will help you decide what would I have done? I don't know. And so you can relearn it here and then apply it to the rotation. Like I said, it does get a little harder because we got to do the equations for both translation and rotation. Then we have to think about the connection between them. So now we have two objects. And you can imagine how complicated this could get if we have one object that is both translating and rotating. There's a lot of equations. And another object that is translating and rotating. And then the connection between them. And, what's wrong with 7 equations, 7? No, it won't get that bad. Okay. But that's the idea. Write out the equation. Stick to the principles. Don't try to force it into something it's not. Just start with that very simple, fundamental idea. Well, finally, now that my overhead has gone down, as I was trying to get to the next one then. And the next one's very similar to this one we just did. The setup is a little different looking. It's number 49. And number 49 here, 7th edition, chapter 10, problem 49, looks a lot like this crazy apparatus that you saw me working with and what you'll see in the lab today. Because here'll be our equation, if you will. What we're trying to do is to find out what is the rotational inertia of. And really the first thing we'll do in lab is we'll just put the disk on here. And so forget that little object sitting on top, but they're showing an example of how NASA tests the rotational inertia of its satellite. It takes a little platform, puts the satellite and spins it, and see how easy or hard it is to spin it to find out what is the rotational inertia of the satellite. Ours will be a little simpler than that. We're not going to put a satellite on here, but we're going to put a disk on here and find out what is the rotational inertia of the disk. And then after we put the disk, we'll put a ring on it, so we'll get the disk and the ring. And so if we get the total, we could subtract off what we did before the disk. So the first time we do it, we'll get the disk. The next time we do it, we'll get the total. Then if we subtract off the disk from the total, we'll get the hoop. And so before the lab's over, we'll have an experimental measure of what is it for a disk, what is it for a hoop, does it agree with our calculations for a disk and a hoop. And then we'll do a part 3, which I won't explain now. I'll wait for the lab there. But here is the problem. So if I read number 49, it says this. This problem describes one experimental method of determining the moment of inertia of an irregularly shaped object. And the reason they throw irregular, sometimes this could just be such a complicated shape is, do you really want to calculate it, or can you calculate it accurately? Might be a tough question. So instead of calculating, it's, hey, hook it up, see what it comes out to, you know, measure it. And that's what this one is describing. So an irregularly shaped object, such as a payload for a satellite. Now, figure 49 shows a counterweight of mass little m is suspended by a cord wrapped around a spool of radius little r, forming part of a turntable that is supporting the object. The turntable can rotate without friction. Using the counterweight, it is released from rest. It descends through a distance of h. It acquires a speed v. It has a moment of inertia of I. Show that the moment of inertia I is given by this equation. And let me, in the short time we have, not write down the actual equation, but there's the idea. Could you find out an equation that says I equals from this, given a speed? And so I think you see it's a lot like this problem. The setup is a little different. It's kind of harder to draw, and that's why I wanted the picture. But what I have then is I have a free body diagram, or I have some rotations going on here. And so let's see what this comes out to be. Now they are really asking it in terms of energy. So I'll attack this one in energy. I only say that because then I'm going to do it a second time for you when we get into lab, and then that time let's do it in terms of forces and torques. So let's do it both ways. Let's do it this problem in terms of energy, and let's do it again in the lab, and hopefully by me doing it a couple times different ways, it'll make sense to you and you'll be able to come in for the test and ace the test. I can't believe we have a test in 2 days. That's oh, you guys are listening. Okay, no. I don't know when our test is. It's not 2 days, though. Gonna make us all look now, right? Your test is scheduled for the 16th, and we're a little behind. I guess I should probably debate with you if you want to do it the next week in there too, but then we got to rush the last chapter, although those are probably better rushed than these. So those are easy compared to these chapters. All right, so let's work on this problem. So I think you got the idea. Let me not draw the whole picture again, but it's really the same idea that if this drops a distance h, what is I related to? So if I did my conservation of energy, I would say, all right, and I'll just put here number 49. What I would say is mgh. So as this thing goes down, just like we saw in the problem before this is going to lose gravitational potential energy. So it becomes mgh. Okay? Where does it go? Well, as you just pointed out, doesn't it go to two places? It goes to 1/2 mv squared and 1/2 I omega squared, right? So it goes to two pieces. The translational kinetic energy is because this one's going to have some of the energy, and the other energy is going to be from that thing rotating. Okay? And so if I keep working on this, I will put the 1/2 v squared plus 1/2 I, but it's this part where my v over r is equal to omega, right? Isn't that the connection? But here's what I want you to be careful, and I'm disappointed that the picture doesn't show it. What's r? Because there's a bunch of r's up here. I would say there's a radius of this cylinder. Is that it? Yeah, I would say there's a radius of that pulley. Is that it? I would say there's a radius of this shaft here. Is that it? I would say there's a radius of this base up here. Is that it? I would say there's a radius of that satellite. Is that it? And it sounded like, and most of you were right, it's this. And I must admit, in the lab we do, that's probably the most confusing. People want to pick the r to be the radius of this hoop up here, or maybe the radius of this disc up here. Is that what the r is? No, it's down here. It's where the string is tied to. Why? Right, because if I want this v to be the same as this v, what I am saying is, if this is the v of this one, then this would be the speed of the string. The speed of the string would be the speed of the points tied to here, so that must be the radius of those points. It's not the radius of this one or this one or this one, it's the radius of where that string is wrapped around. Okay? And in the big one that I did earlier that treated this reel, we wrapped the string around the outside. And so the radius of the reel and the radius of where the string was tied was the same thing. But it's not in this case. So we need to be careful here and pay attention to which one do we mean. So this is then the radius of what your author calls the spool. I like to call it the part where the string is tied to. All right. So I'm going to make that step and put a v squared over an r squared. Then it's just a little bit of math here. I mean, we can bring the 2 to the other side, so this becomes a 2, an m, g, and an h here. Let's see, that leaves us with an m if we factor out a v squared. So there's the 2, there's the v, there's the m, I got the 2. This could be then an I over an r squared. And so, oh, my apologies. We're not solving for v like we did last time. This one is saying solve for I. Okay, so let me solve for I. I'll still bring the 2 over, 2mgh. But once I do that, I will then subtract the mv squared and then have an I, a v squared over an r squared. And so then, if I bring the r squared and the v squared over, 2mgh minus mv squared equals I get my little formula. Although it doesn't quite look like theirs, what do? They do 2 more steps. They then factor out an m. So this becomes a 2gh minus a v squared. And then they also put the v squared inside here, so that this becomes an mr squared. And then we got the 2gh over v squared minus 1. And I hope that's what I got there. 2gh divided by v squared. Yeah. And so they used conservation of energy. Okay, so once we did those other two problems, it hopefully didn't look hard. I did want you to see it. I did want you to see that connection between the R of the spool and the R of the radius it, because that's where students make their biggest mistake in the lab we're about to do here. And I'm going to emphasize that again. I want to go through these exact same things, but then I'll use torque and acceleration and come up with exactly the same thing and see what you get in lab. Oh, next one. Throw one more out here at you. I think that's all we'll have time for. Bummer. Should I do 71, 72, 65? Yeah, let's do 65. Number 65. We'll just do 65 here and get it. And they have a nice picture of this one, although I'm not sure this one is quite complicated enough to need a picture, but as long as I already got it turned on there and showing it, here's what they have. They say, in number 65, they say a long uniform rod of length L and of mass capital M can pivot around a horizontal frictionless pin at one end of the rod. The rod is released almost from rest in its vertical position as shown in figure 65. At the instant the rod becomes horizontal, find its angular speed, its magnitude of acceleration, the x and y components of the acceleration of the center of mass, and D, the components of the reaction force at the hinge. All right, well, there's a lot to ask there, but maybe we can do it in 5 minutes. Let's go with A. A is kind of the simplest one here. What is the angular acceleration? Do you catch that's an energy problem? They're asking for speed and they give us angle, distance it moves, right? They're not giving us time and acceleration. So I would say, well, my beginning energy equals my ending energy. I picked this one on my list because this one is a continuous object. And so when it goes down, where do you want to call y equals to 0? Here? So what height does it start at? L? L over 2. It's its center of mass. We got to go back to that center of mass. So I'd say this is mg L over 2. Don't miss that, right? What is its initial height? Center of mass. That's why we did all that in chapter 9, where we gave our object, our extended object size and the center of mass. So the center of mass of the object is right here, and then the center of the mass is here. So the center of mass is at height 0. It starts at L over 2. Where does the energy go? Well, it goes into 1/2 I omega squared, right? It goes into a rotation. Is this thing rotating or translating? Yeah, I'd say it's rotating. Now this one's a little different, also why I picked it. It's not rotating about its center, it's rotating about its end point. So, as I go to write this out, and I say mgl over 2, and I bring this 2 over, and I bring the I over, and I get my omega squared and take its square root. That would be the equation for what is its angular speed. And then fortunately the 2's cancel off there. And so I would have an m, a g, and an l divided by I. And that's what this first part is saying. What is the angular acceleration? But here's a tough one too. What is I? Well, we did this one for a rod, like last Wednesday. And I'm sure you committed it to memory. So what is it? It was 1/12, wasn't it? About its center. Is this rotating about its center? No, so how do we get it off of its center? That parallel axis theorem, exactly. So this needs to be a 1/12 ml squared plus, and how far are we moving from its center? L over 2. So this would be ml over 2 squared. And so we've got the L in the numerator still. But in the denominator, we have a 1/12 and a 1/4. That makes a 1/3. So that's 1/3 ml squared. You might even remember 1/3 because we actually did this one in class. We did what was the rotational inertia about its end point. Twice, actually. Once we just calculated, another time we used it to show the parallel axis theorem. Well, once you do that, then you can see how one of these L's cancels off, this M cancels off, and so the final part of A anyway, G, G over L. And so that would be the angular speed at that point. And I guess we can't answer the other ones for today. So we'll stop there and go into chapter 11 on Wednesday. So work on the